Imagine a box sealed and silent. Inside there is a cat. Alongside the cat sits a device of diabolical ingenuity, a single radioactive atom linked to a Geiger counter. This counter is in turn wired to a hammer poised to shatter a vial of poison. If the atom decays, an event governed entirely by the bizarre probabilistic laws of the quantum world, the hammer will fall, the poison will be released, and the cat will perish. If the atom remains stable, the cat will continue to nap blissfully, unaware of the existential blade upon which its life rests. You cannot see inside. You cannot know. So what is the state of the cat, our intuition forged in a world of solid objects and definite outcomes, screams that there can only be two possibilities. The cat is either living or it is dead. It is a simple binary choice. But in the strange, shimmering ghost realm of quantum mechanics, the universe offers a third, far more unsettling answer. Until we open that box, until we times observe times the system, that single atom exists in a state of pure potentiality. It has both decayed and not decayed simultaneously. It lives in a ghostly blur of all its possible futures at once. And if the fate of the atom is a blur, then what does that mean for the cat whose very life is chained to it? According to the cold, hard mathematics that underpins our reality, the cat itself must also exist in this impossible state. It is a spectre of being and non-being. It is a quantum ghost, both purring with life and still with death locked together in an inseparable paradoxical embrace. This is the profound, maddening and iconic thought experiment of Schrödinger's cat. It was conceived not as a genuine proposal for an experiment, but as a scream of protest. In the early 20th century, a brilliant generation of physicists, men like Niels Bohr and Werner Heisenberg, were peering under the hood of reality for the first time. What they found was not the clockwork predictable universe of Newton, but a chaotic, uncertain world of probabilities and waves of chance. They found a place where a particle could be in multiple places at once, where it could tunnel through solid barriers as if they were smoke, where the very act of looking at something changed what you saw. This new science, quantum mechanics, was unbelievably successful. It predicted the behavior of atoms with staggering accuracy and would go on to power our modern world from the laser in your Blu-ray player to the transistors in your smartphone. Yet for some of its pioneers, including the brilliant Austrian physicist Erwin Schrödinger, the philosophical implications were a bridge too far. He could accept the mathematics for the subatomic world, this hidden realm of electrons and photons, but he was horrified by the idea that its bizarre rules could leak out, that they could infect our everyday macroscopic reality. He devised his famous feline paradox in 1935, not to celebrate this new physics, but to ridicule it. He was essentially shouting at his colleagues, look at the absurdity your theories lead to. If your superposition of states is real for an atom, then it must be real for a cat. And that is patently insane. He intended to expose a deep flaw in the logic, to show that there must be a dividing line, a sacred boundary between the fuzzy, uncertain quantum world and our solid, dependable classical one. He wanted to prove that a cat could not, under any circumstances, be both alive and dead. But history and physics had a surprise in store for him. Schrödinger's reductio ad absurdum failed. Instead of disproving the theory, his thought experiment became its most famous, most powerful illustration. He had inadvertently created the perfect metaphor for the central mind-bending mystery of quantum mechanics, the principle of superposition. This is the radical idea that a physical system, an atom, an electron, and yes, even a hypothetical cat in a box can exist in a combination of all its possible states at the very same time. It is not that we simply don't know the state. That would be a problem of simple ignorance. This is a far deeper, more fundamental truth about the nature of existence itself. Before an observation is made, the particle's reality is not a single concrete fact waiting to be discovered. Its reality times is times the probability cloud. It is the sum of all possibilities. The electron is not in position A times or times position B. It is in a very real sense in position A times and times position B, and every point in between. The atom has both decayed times and times not decayed. This isn't a metaphor. It is the bedrock of how the universe operates, at its most fundamental level. We are used to a world of definite answers. The train is on this track or that one. The coin has landed on heads or on tails. The light switch is on or it is off. Our language, our logic, our very consciousness evolved to navigate this world of either or. Quantum mechanics whispers of a deep, stranger reality built on both, and it is a reality woven from maybes. Imagine a single particle, an electron, fired at a screen with two narrow slits. In our world, a solid object like a marble must pass through one slit or the other. There is no alternative, but an unobserved electron does something impossible. It behaves not like a particle at all, but like a wave. It spreads out, passing through both slits simultaneously, interfering with itself on the other side to create a pattern of light and dark bands, a pattern that could only be formed if something went through both paths at once. The electron, in its state of superposition, explored every possible route. It is only at the moment we try to measure which slit it went through, the moment we place a detector and ask the universe for a definite answer, that the magic vanishes. The instant we observe it, the wave of possibility collapses into a single concrete reality. The electron suddenly chooses a slit, behaving once more like a well-behaved, predictable marble. The interference pattern disappears, replaced by two simple clumps, just as we would expect. The very act of looking, of measuring, of knowing, seems to force the universe to pick a side. This brings us back to that silent, sealed box. The superposition of the atom decayed and not decayed is directly linked to the superposition of the cat alive and dead. The entire system is one entangled quantum state, a single vast wave of probability, and it remains in this ghostly, indeterminate condition until a measurement is made. In this case, the measurement is the act of opening the box, of letting the light flood in, of an observer peering inside to learn the cat's fate. At that exact moment, and not a moment before, the universe appears to roll its cosmic dice. The wave function collapses. The blur of possibilities resolves into a single, stark, classical fact. The atom is now definitively decayed or definitively not decayed. The Geiger counter has clicked or it is silent. And the cat is now finally either alive or dead. But this raises the most profound question in all of science, a question that haunted Schrödinger and continues to baffle physicists and philosophers to this day. What constitutes an observation? What is this seemingly magical power that can reach into the quantum realm of infinite potential and crystallize it into a single mundane reality? Does it require a conscious mind? Was it my own act of looking that forced the cat into a definite state? Would a camera recording the event be enough to collapse the wave function? Or what about the Geiger counter itself? Is times an observer, a complex enough system to break the spell? Where is the line drawn? At what point does the weirdness of the quantum world stop and the certainty of our world begin? Schrödinger, with his unsettling thought experiment, had stumbled upon the measurement problem, the great unresolved schism at the heart of quantum theory. He had hoped to wall off a subatomic world, to keep its probabilistic ghosts confined to the basement of reality. Instead, he shattered the wall between the world of the very small and the world of the very large. He showed us that in principle, the strange rules that govern a single atom could be amplified until they held a living creature in a state of suspended animation between being and nothingness. He forced us to confront the possibility that the solid, stable reality we perceive is not the fundamental truth. Perhaps it is just an illusion, a consensus reached only when a measurement is made. Perhaps the universe in its unobserved state is a seething, infinite ocean of overlapping possibilities, a symphony of every might be, and could have been all playing out at once in a grand, silent superposition. And perhaps we, the observers, are the conductors of this cosmic orchestra, our every glance and measurement forcing a single note to ring out from the cacophony, creating the melody that we call reality. This isn't just philosophical navel-gazing. Understanding superposition and how it transforms into the world we know is the single greatest challenge in modern physics. The answers have staggering implications not just for our technology, but for our understanding of existence, of time, of causality, and of our own place in the cosmos. Is there just one outcome when the box is opened? Some interpretations of quantum mechanics, like the many worlds theory, suggest that there is no collapse at all. Instead, reality itself splits. In one universe, you open the box and find a living cat. In another parallel universe, a version of you identical in every way opens the box and grieves for a cat that has died. Every quantum coin toss, every atomic decay, every possible outcome branches off to create its own complete, consistent reality. A vast, ever-expanding multiverse of possibilities made real. It is a staggering, almost terrifying idea that every choice, every chance spawns entire new worlds. We are left standing before that sealed box, but the box is now the universe itself. And the cat inside is the very nature of reality. For a century, we have been wrestling with the ghost that Schrödinger let out of the bag. We have learned to harness its power, building quantum computers that can exist in a superposition of states to perform calculations that would take a classical computer billions of years. We use its principles to build medical imaging devices, to create unhackable communication networks, to design new materials atom by atom. We have learned to put the paradox to work. But the central mystery remains. We have the equations we can make, the predictions we can build, the technology. Yet we still do not truly understand what is happening under the surface. We do not know why the act of observation holds such a pivotal, almost mystical power. We do not know if reality is a single story constantly being updated, or an infinite library of all possible stories being written at once. The cat in its terrible quantum limbo continues to mock us with a riddle that strikes at the very heart of what it means to be, to know, to exist. To solve it, we cannot simply stay outside the box. We must venture inside. We must journey back to the dawn of the quantum age, to meet the minds that first dared to peek behind the curtain of classical reality. We must explore the strange landscapes they discovered, landscapes where particles are waves, where uncertainty is a fundamental law of nature, and where two objects can be mysteriously linked across the entire expanse of the universe. We must dissect the very act of measurement, the fulcrum upon which all of reality seems to pivot. Our journey begins not with an answer, but with that profound and unsettling question whispered from a sealed container of poison and potential. What is real when no one is looking? For nearly 3 centuries, we thought we had solved the universe. From the time of Isaac Newton, reality seemed to be a magnificent, intricate clockwork mechanism, wound by a divine hand and left to run its course. Every gear turned with perfect predictability. Every planet followed a path etched into the fabric of space-time, a path we could calculate with breathtaking precision. If you knew the position and momentum of every single particle in the cosmos at one instant, you could, in principle, know the entire past and predict the entire future. It was a universe of certainty, a place of comforting absolute laws, where cause led inexorably to effect. There were no hidden variables, no cosmic sleight of hand. The universe was an open book and physics was its language. We were simply learning to read. We built our steam engines, our bridges, our entire industrial world on this solid foundation of determinism. The feeling was one of mastery, of profound understanding. We believed we were standing at the sunlit summit of knowledge, with only a few minor clouds lingering on the horizon, small, bothersome details that would soon be swept away by the next brilliant calculation. But those clouds were not wisps of smoke. They were the harbingers of a hurricane, a storm that would not just rattle the foundations of physics, but pulverize them into dust. And it all began not with a bang, but with a quiet, stubborn glow. The problem was something as simple as a furnace or a piece of heated iron. As any blacksmith knows, when you heat a metal, it first glows a dull red, then a brighter orange, then yellow, and finally a brilliant white-hot blue. Classical physics could explain the red and yellow parts of the spectrum perfectly well. But its equations, the very laws that charted the motions of the stars, predicted something utterly insane. As the object got hotter, it should radiate more and more energy at shorter and shorter wavelengths, past blue, past violet, and into the ultraviolet. According to the flawless mathematics of the 19th century, a simple glowing coal should unleash an infinite amount of energy at these high frequencies. An infinite energy blast from a teacup. It was a prediction so violently at odds with reality that it was nicknamed the ultraviolet catastrophe. For the greatest minds of the age, this wasn't just a small error. It was a deep philosophical crisis, a crack in the very bedrock of their understanding. The universe at its most fundamental level was refusing to obey the rules. Into this paradox stepped a reluctant revolutionary. Max Planck was a man steeped in the classical tradition, a conservative physicist who revered the old masters and had no desire to tear down the edifice they had built. He wrestled with the ultraviolet catastrophe for years, trying every conventional method to resolve it, to tame the infinite energy his colleagues' theories predicted. He failed. Finally, in a moment he would later describe as an act of desperation, he decided to try something that went against all his training and intuition. He cheated. He proposed that energy was not a smooth, continuous flow like water from a tap. What if he wondered energy could only be emitted or absorbed in tiny, discrete packets, like grains of sand instead of a flowing dune, like individual coins instead of a river of molten gold? He called these indivisible little energy packets quanta. He didn't truly believe in them himself. He saw it as a purely mathematical trick, a fudge factor to make the equations work. But when he plugged this radical assumption into his calculations, the ultraviolet catastrophe simply vanished. The maths suddenly miraculously matched the real world. By making energy lumpy and granular, he had solved the puzzle. Planck had stumbled upon a new fundamental constant of nature, a number now known as Planck's constant, which defined the size of these energy packets. He had unknowingly unearthed the cornerstone of a new reality, but he was terrified by what he had found, hoping someone else would come along and find a more sensible classical explanation. That someone else was a young, unknown patent clerk in Bern, Switzerland. While Planck had seen his quanta as a mathematical convenience, Albert Einstein saw a profound truth about the nature of light itself. He turned his attention to another nagging puzzle of the era, the photoelectric effect. Scientists had known for decades that if you shine a light on certain metals, they will spit out electrons. The old wave theory of light suggested that a brighter light, a more intense wave, should eject electrons with more energy, but experiments showed this wasn't true. A brighter light only ejected more times electrons, but their energy remained the same. It was the color times of the light, its frequency, that determined the energy of the ejected particles. A faint blue light could kick out electrons with far more energy than an intensely bright red light. It made no sense. It was like a gentle ripple in a pond hitting the shore with the force of a tsunami, while a towering tidal wave produced only a harmless splash. Einstein, in his miracle year of 1905, provided the stunning answer. He took Planck's desperate idea and declared it to be a physical reality. Light, he argued, was not a continuous wave at all. It was a stream of Planck's energy packets. These tiny bullets of light, later named photons, carried a discrete amount of energy determined by their frequency. When a photon strikes an electron in the metal, it's a one-to-one collision. A single photon gives all its energy to a single electron. This is why a brighter light, which is just more photons, knocks out more electrons but doesn't make any single electron more energetic. To do that, you need a different kind of ammunition. You need a higher frequency photon, a blue or violet bullet which carries a bigger individual punch. In one breathtaking stroke of genius, Einstein had demonstrated that light, which for centuries had been the quintessential example of a wave, was also undeniably a particle. The first pillar of the quantum paradox wave-particle duality had been erected. The comfortable, sensible world of classical physics was beginning to look very strange indeed. The revolution now spread from the nature of energy to the very structure of matter. For years, the atom had been imagined as a miniature solar system, a dense central nucleus, the sun orbited by tiny electrons, the planets. It was a beautiful and intuitive model proposed by Ernest Rutherford, but it harbored a fatal flaw. According to the established laws of electromagnetism, an orbiting electron is an accelerating charge, and an accelerating charge must constantly radiate away energy in the form of light. This isn't optional, it's a law. As the electron loses energy, its orbit should rapidly decay. In less than a trillionth of a second, every electron in every atom should spiral into its nucleus, bringing about the instantaneous collapse of all matter in the universe. The fact that you are here, that the chair you're sitting in exists, that the stars continue to shine, was a profound and terrifying mystery. The classical atom was fundamentally and catastrophically unstable. The man who would save the atom was a brilliant young Dane named Niels Bohr, a thinker whose mind seemed perfectly attuned to this new, bizarre quantum logic. He travelled to England to work with the pioneers of atomic physics, and he brought with him the radical ideas of Planck and Einstein. Bohr proposed a model of the atom so audacious it bordered on heresy. He suggested that electrons could not orbit the nucleus just anywhere they pleased. Instead, they were restricted to a set of specific allowed orbits, like planets locked onto invisible tracks. Each track corresponded to a specific energy level, a quantum state. As long as an electron remained in one of these special orbits, it was exempt from the laws of classical physics. It simply would not radiate energy. Its stability was guaranteed by a new quantum rule. But an electron could, he proposed, jump from one orbit to another. If it jumped from a higher energy orbit to a lower one closer to the nucleus, it would emit a single photon of light, a quantum of energy whose color was precisely determined by the difference in energy between the two tracks. Conversely, it could absorb a photon and leap to a higher orbit. This was the birth of the quantum leap. It was not a journey. The electron was not seen to travel through the space between the orbits. In one moment it was here, in the next it was there. Instantly, it dematerialized from one state and reappeared in another without ever existing in between. This bizarre, discontinuous behavior perfectly explained the strange spiky spectra of light emitted by different elements, why hydrogen glows with specific shades of red and blue and sodium with its characteristic yellow. Each color was the signature of a specific quantum leap within the atom. Bohr had rescued the atom from collapse, but at a tremendous cost to our intuition. He had injected the quantum's granular, discrete nature into the very heart of matter. The universe was not a smooth continuum. It was a place of forbidden zones and instantaneous jumps, a reality built on a ladder of permitted states, with nothing but empty, impossible voids in between. The clockwork was not just broken, it was being replaced by something that operated like a magical staircase. The world of physics was reeling. Light was both a wave and a particle. The atom was a place of impossible, instantaneous leaps. The weirdness was escalating, but the next step would push the human mind to its absolute limit. It came from an unlikely source, a young French prince named Louis de Broglie, who was writing his doctoral thesis. De Broglie was captivated by the symmetry he saw in Einstein's work. Nature, he felt, ought to be beautiful and balanced. If a wave like light could have the properties of a particle, then could it be, he wondered, that a particle like an electron might have the properties of a wave? It was a question of breathtaking audacity and childlike simplicity. He proposed that every moving particle in the universe, from the smallest electron to you, to the planet Earth itself, has a wave associated with it. A matter wave that guides its motion. He even derived an equation for its wavelength. For large objects like us, this wavelength is so infinitesimally small as to be completely undetectable, which is why we never see a person diffracting as they walk through a doorway. But for a tiny particle like an electron, the wavelength is significant. It's comparable to the size of the atom itself. De Broglie's idea was so strange that his examiners were unsure whether to grant him his PhD. They sent his thesis to Einstein for an opinion. Einstein's response was immediate and enthusiastic. He recognized the profound, unifying beauty of the concept. It was not just a clever idea. It explained Bohr's mysterious atomic model. If an electron was a wave, then for it to exist in a stable orbit around a nucleus, it had to form a standing wave like a plucked guitar string. Its circumference had to be a whole number of its wavelengths. Any other orbit would result in the wave interfering with itself and cancelling out. The electron wave could only fit in certain resonating orbits. Bohr's arbitrary magical rules were not rules at all. They were the natural consequence of the electron behaving as a wave. The idea was soon confirmed by experiment. Beams of electrons, when fired at a crystal, were seen to diffract and create interference patterns, the telltale signature of waves. The conclusion was inescapable, and it was shattering. Every single particle of matter in the cosmos is also simultaneously a wave. Wave-particle duality was not a quirk of light. It was the fundamental schizophrenic nature of everything. And this is where we must abandon all our classical intuition, all our notions of a solid, definite reality. This is where we arrive at the central mystery, the ghost in the machine of the quantum world superposition. If an electron is a wave, then what does that even mean for its location? A wave is not in one place. It's a disturbance of vibrations spread out through space. A wave on the ocean doesn't have a single precise position. It is a region of rising and falling water, and so it is with the electron. Before you measure it, before you interact with it in any way to pinpoint its location, the electron does not have a definite position. It exists as a wave of probability. Its wave-like nature means it is literally in many places at once. It is not that we simply do not know where it is. It is that the electron itself has not decided. Its existence is smeared out a ghostly cloud of potential, a shimmering superposition of all the possible places it could be. Think of it as a spinning coin. While it is in the air, it is neither heads nor tails. It is a dynamic, blurry combination of both possibilities. Only when it lands, only when it is measured by the table, does it collapse into a single, definite state, heads or tails. The quantum particle is like that spinning coin, but the possibilities are far more vast. An electron can be in a superposition of positions, a superposition of energy, states, a superposition of spins. It is a symphony of potentialities, all coexisting simultaneously in a strange ethereal harmony. This isn't a metaphor. According to the mathematics of quantum mechanics, this is the literal truth. The fundamental constituents of our universe, when we are not looking at them, exist in this shadowy, indefinite realm of pure potential. They are a blur of maybes. This revolutionary idea meant that at its core, the universe was no longer deterministic. It was probabilistic. You could no longer predict with certainty what an electron would do. You could only calculate the probabilities for all its possible outcomes. This discovery was the final fatal blow to Newton's clockwork dream. The very language of physics had been forced to change from the crisp, certain language of is to the hazy, statistical language of probably. This radical uncertainty horrified many of the theory's own creators. Einstein himself would famously object, refusing to believe that the universe was governed by cosmic chance, proclaiming that God does not play dice. A deep schism was opening between the old guard and the new quantum pioneers. They had created a theory of unparalleled predictive power, one that would underpin all of modern technology, from lasers to computers. But they had also unleashed a philosophical monster. They couldn't agree on what it all meant. What happens when we make a measurement? Why does our act of looking at this blurry cloud of possibilities force reality to make a choice, to collapse the wave of potential into a single concrete actuality? What is the role of the observer in creating the world we see? The very foundations of reality had been replaced with a fog of probability, and at the heart of that fog lay a profound and disturbing question, a paradox that would come to be embodied by a cat, a box, and a vial of poison. And so the new physics offered us a universe built not on solid certainties, but on a shimmering, delicate haze of possibility. A world where a particle is not a thing but a whisper of potential. A ghost that can haunt multiple locations at once. For a generation of young, audacious physicists, this was intoxicating. It was a revolution not just in science, but in thought itself. They had pried open the clockwork of the cosmos and found not gears and levers, but a cloud of phantoms. But this radical new vision was not a celebration for everyone. For some of the very minds who had laid its foundations, this emergent picture of reality was becoming a nightmare. A profound schism was opening a philosophical chasm that would divide the greatest intellects of the 20th century. On one side stood the architects of this new quantum world, Niels Bohr and Werner Heisenberg, championing their Copenhagen interpretation, a pragmatic, almost mystical view that what we cannot measure, we simply cannot know, and perhaps should not even ask about. On the other side stood a titan, a man whose name was synonymous with genius, who had himself rewritten the laws of space, time, and gravity, Albert Einstein. For him, this was not progress, it was a surrender. The universe he had revealed was majestic, orderly, and knowable. Its laws were written in an elegant universal language. There was a reality, an objective, independent truth that existed whether we were looking at it or not. The moon, he famously quipped, was there even when nobody looks. But this new quantum theory suggested something deeply unsettling, something that struck at the very heart of his scientific faith. It proposed a universe governed not by definitive cause and effect, but by the capricious roll of cosmic dice. Einstein found this notion utterly abhorrent. His lifelong quest was to read the mind of God, to uncover the deep, immutable logic humming beneath the surface of existence. And he would not accept that at its most fundamental level the universe was nothing more than a high-stakes game of chance. His famous declaration, "God does not play dice," was not a witty retort. It was a cry of anguish, a rebellion against a reality that seemed to be dissolving into a fog of statistical noise. He saw the Copenhagen interpretation as a tranquilizing pill for physicists, a way to avoid confronting the terrifying absurdity their equations implied. For Einstein, a theory that could only predict probabilities was not a complete theory. It was a sign that we were missing something, some deeper hidden layer of reality that would restore order and certainty. The heart of this conflict, the epicenter of this intellectual earthquake, was a maddeningly simple and yet impossibly complex question. What actually happens when we look proving? This is the measurement problem, the great unsolved riddle of quantum mechanics, a puzzle that haunts physics to this very day. It begins with an elegant and powerful piece of mathematics, an equation that was ironically devised by another brilliant physicist who would soon join Einstein in his philosophical descent, Erwin Schrödinger. His equation describes something called the wave function. Think of the wave function not as a physical wave in an ocean, but as a wave of pure information, a wave of potential. It is the complete mathematical description of a quantum system, and it contains within it every single possible outcome, every possible location, every possible spin, every possible energy state, all held in a delicate, shimmering balance of superposition. Before you look, that electron is not in any one place. It is in a very real sense a cloud of everywhere at once, a phantom defined only by Schrödinger's mathematical ghost. It is a symphony of maybes, a chorus of potentialities, singing in perfect, unresolved harmony. This wave function evolves through time, with beautiful deterministic precision following the rules of its equation perfectly. As long as the system remains isolated, untouched, unobserved, its future is a predictable, evolving tapestry of possibilities. But the moment we intervene, the moment we try to times something, the moment we perform a measurement, something violent and mysterious occurs. That beautiful, flowing wave of infinite possibilities instantaneously and inexplicably shatters. The symphony of maybes falls silent, and a single solitary note rings out. The cloud of potential evaporates, and in its place a single concrete reality snaps into view. The electron is times here asterisk. Its spin is times up asterisk. Its energy is times this asterisk. This sudden jarring transition from a superposition of many states to a single definite state is what physicists call the collapse of the wave function. It is the act of creation, a moment where the universe seemingly makes up its mind, forced into a decision by the simple act of our observation. This is the measurement problem. What is this collapse? Where in the laws of physics is this process? Described Schrödinger's own equation, the very tool used to describe the wave function, contains absolutely no mathematics for its own collapse. It's as if the most important chapter of the cosmic rulebook is simply missing. The laws of quantum mechanics describe the before with perfect clarity, the smooth, wave-like evolution of possibilities. And they allow us to calculate the probabilities of the after, the chance of finding the particle in any given state. But the in-between, the how, the bridge from potential to actual, is a void, a frightening philosophical black box. Niels Bohr and his followers in Copenhagen proposed a startling solution. They essentially cleaved reality in two. There is the strange, ghostly quantum world of atoms and particles governed by the probabilistic wave function. And then there is our world, the large-scale classical world of laboratories, scientists and measuring devices, governed by the familiar laws of certainty. For Bohr, a measurement was simply the moment of interaction between these two fundamentally different realms. When the quantum system touches our classical instrument, the rules of the game abruptly change. the wave function collapses. That's it. Don't ask why, don't ask how. It is a fundamental postulate of the theory, an axiom you must accept to proceed. To Bohr, asking what the electron was really doing before we measured it was a meaningless, unscientific question. The job of physics, he argued, is not to describe what reality times is times, but only to describe what we can times say, times about reality through our experiments. It was a powerful, pragmatic, and deeply unsatisfying answer. It implied that the very act of observation plays a uniquely privileged role in the cosmos, that we, the observers, are not passive witnesses to the universe, but active participants in the creation of its reality. The world, it seemed, only solidifies into definite form when we deign to look at it. This was the idea that chilled Einstein to the bone. It placed humanity, or at least our measuring apparatus, at the center of existence in a way that felt pre-Copernican. It replaced objective reality with a strange observer-dependent shimmer, and it led to an even more troubling question. What exactly constitutes an observer or a measurement? Does it require a conscious human being with a PhD in physics? Does a camera count? What about a simple Geiger counter, a purely mechanical device? If a Geiger counter clicks has the wave, the function of a radioactive atom collapsed. Or does the Geiger counter itself, along with the atom, to enter a ghostly superposition of having both clicked and not clicked, waiting for a conscious mind to look at its dial to resolve the ambiguity? Where do you draw the line? This is the infamous Heisenberg cut, the arbitrary boundary that Bohr's interpretation forces us to draw between the quantum and the classical. But there is no line. The universe is not two separate kingdoms. Our measuring devices, our laboratories, our own bodies are all made of the very same quantum particles they are intended to measure. We are, all of us, enormous, complex collections of atoms obeying the same fundamental laws. There is no classical world and quantum world, there is only one world. So, how does a system made entirely of quantum particles, which should itself be described by a giant complex wave function, somehow gain the magical ability to collapse the wave functions of other particles? This was the intellectual precipice upon which physics found itself. The theory was undeniably successful, its predictions stunningly accurate. It powered a revolution in technology, giving us lasers, transistors, and the foundations of the digital age. Yet at its heart lay a philosophical poison, a paradox so deep it seemed to challenge the very definition of reality itself. The majority of physicists swept up in the excitement of discovery were content to follow Bohr's advice: shut up and calculate. The equations worked, and that was enough. But for a stubborn few, for the keepers of the philosophical flame, this was an unacceptable compromise. And among them, a new voice of dissent grew louder. Schrödinger, the quiet intellectual Austrian, the man whose equation was the very bedrock of this new science. He was not an outsider throwing stones like Einstein. He was an architect horrified by the strange temple being built upon his foundation. He had given the world the elegant mathematics to describe quantum waves, only to watch Bohr and Heisenberg interpret them in a way he found repellent. He called the idea of quantum jumps, the instantaneous collapse, a monstrosity. He felt his colleagues were not solving the mystery, but simply agreeing to ignore it, hiding their confusion behind a veil of pragmatic philosophy and impenetrable mathematics. Schrödinger believed the Copenhagen interpretation was not just incomplete, it was absurd, and he decided that the only way to expose this absurdity, to force his contemporaries to truly confront the madness they had unleashed, was to take their logic and follow it to its most extreme and grotesque conclusion. He would need to construct a scenario so vivid, so visceral, that no one could dismiss it as mere abstract philosophy. He would scale up the paradox, dragging the ghostly superposition of the subatomic world into our own tangible macroscopic reality. He needed to build a bridge from the quantum realm of the maybe to the classical realm of the is or is not. His plan was to craft a story, a thought experiment, a reductio ad absurdum so powerful it would act as a philosophical bomb. He would chain the fate of a familiar living creature directly to the probabilistic whim of a single unobserved atom. By doing so, he would force the weirdness out of the theoretical shadows and into a place where it could not be ignored. He would take the core tenet of the Copenhagen view that a system remains in all possible states until it is observed and apply it not to an invisible electron, but to something undeniably heartbreakingly real. Something caught in a terrible limbo, suspended by the laws of quantum mechanics, in a state that defies all logic, all intuition, and all compassion. He would imagine a sealed box. Inside this box, he would place a diabolical device, a mechanism linking the quantum world to the world of the living. And with this terrible invention of the mind, he would pose a single devastating question to his colleagues, a question that would echo through the halls of science for a century to come. A question about a cat, a vial of poison, and the very nature of existence itself. What he was about to unleash was not an experiment to be performed, but an argument to be reckoned with. A stark and unsettling parable designed to show the world the terrifying philosophical price of quantum mechanics. But for all its predictive power, for all the elegant certainty of its equations, this quantum strangeness has felt contained. We have kept it safely locked away, confined to the ghostly realm of the infinitesimally small. It is a set of rules for electrons dancing in their orbitals, for photons choosing their paths for a subatomic world that operates on a logic so alien it might as well be magic. We could accept its paradoxes, a particle that is also a wave, the location that is merely a cloud of probability, because they were times down there, times in a basement of reality we could never visit. We could draw a line, a firm and comforting boundary between that hazy quantum world and our own solid, dependable classical existence. A chair is a chair, a planet is a planet. A cat is either alive or it is dead. There is no middle ground. This very division, this schism in the laws of nature is what tormented the brilliant mind of Schrödinger. He was one of the architects of this new physics, a father of the quantum revolution, yet he found himself haunted by the implications of its most popular interpretation. He could not accept that reality remained a ghostly menu of possibilities until the moment of measurement, the moment an observer intervened and forced the universe to make a choice. To him, this idea felt incomplete, absurd, like a story missing its final page. And so, in 1,935 inches, a series of letters with Albert Einstein, he devised not an experiment of glass and steel, but an experiment of the imagination, a thought experiment, a parable designed to drag the quantum weirdness out of the subatomic shadows and place it squarely, uncomfortably into our world. He was about to build a prison for a paradox, and inside he would place his now famous and famously unfortunate cat. Imagine it with us. A box perfectly sealed, opaque, a cold steel cube that isolates a tiny fragment of the universe from everything else. It is a fortress against information, a pocket dimension governed by its own terrible rules. Inside this metallic prison we place a cat, a living, breathing creature, a complex system of trillions upon trillions of atoms, a being that in our world possesses a definite and unambiguous state of existence. It is warm, it is breathing, it is undeniably alive. But its fate is no longer in its own hands. Its continued existence has been tethered, chained to the whim of a single solitary atom. Alongside the cat we place a mechanism, a diabolical Rube Goldberg machine of quantum chance. At its heart lies a tiny lump of radioactive material, so small that in the span of 1 hour there is a perfect 50-50 probability that just one of its atoms will decay. It is a cosmic coin flip at the most fundamental level. The universe has not yet decided. This atom exists in a quantum superposition, a shimmering blend of two possible states, intact and decayed. It is in the bizarre language of its own reality both at once. Watching this atom is a Geiger counter, an unblinking electronic witness. If it detects the radiation from a decayed atom, that tiny singular particle of decay, it will trigger a relay. The relay is connected to a hammer suspended precariously, a simple mechanical instrument of execution. And beneath that hammer, a fragile glass vial. The vial contains a dose of hydrocyanic acid, a poison so potent that its release would mean instantaneous, irreversible death. The chain of causality is absolute. If the atom decays, the counter clicks. If the counter clicks, the hammer falls. If the hammer falls, the vial shatters. If the vial shatters, the cat dies. We seal the lid. The clock starts. The outside world is now blind. We have no way of knowing what is happening inside. We can't see it, we can't hear it, we cannot gather a single shred of information from that isolated chamber. And in this moment of perfect isolation, the comforting boundary between the quantum and the classical worlds does not just blur, it evaporates completely. Inside the box, the quantum rules, the rules we had safely quarantined to the world, of the atom now begin to spread to infect the entire system like a virus of uncertainty. The fate of the atom is tied to the Geiger counter. The fate of the counter is tied to the hammer. The fate of the hammer is tied to the poison. And the fate of the poison is inextricably fatally entangled with the cat. They are now one single sprawling quantum system. So let us ask the question that Schrödinger wanted the world to ask. After 1 hour has passed, but before we have dared to open the box, what is the state of the cat? Our intuition screams at us. It's a 50-50 chance. The cat is either alive or it is dead. We just don't know which. But this is the great classical mistake. The mistake of assuming our ignorance is the only thing at play. According to the cold, hard and unflinching mathematics of quantum mechanics, our lack of knowledge doesn't mean there is a definite reality hidden from us. It means there isn't one. The atom inside is still in its superposition of being both decayed and intact. Therefore, the Geiger counter is in a superposition of having both detected something and detected nothing. The hammer is suspended in a ghostly state of being both fallen and unfallen. The poison vial is a paradoxical entity, both shattered and whole. And the cat is a quantum spectre. It is not one thing or the other, it is both. It is a creature suspended in a shimmering haze of pure potentiality. Its life and death described by the same wave function, a single mathematical entity that holds both oblivion and existence within it. It is a ghost and a living being entwined, sharing the same space, the same time, the same fur, the same heart that is simultaneously beating and still. Reality inside that box is holding its breath. This is the central, terrifying revelation of Schrödinger's parable. It is the moment the documentary shifts from the theoretical to the visceral. We are no longer talking about an electron's spin or a photon's path. We are talking about life and death, about a being we can picture and understand now, trapped in a state that defies all logic. The absurdity is the entire point. Schrödinger was trying to show that any theory that leads to such a grotesque conclusion must have a piece missing. He believed that this paradox revealed a deep flaw in the Copenhagen interpretation. But instead of killing the theory, his thought experiment became its most powerful, most famous, and most deeply unsettling illustration. It forced us to confront the abyss that had opened up at the feet of physics. Because the spell is not broken, the paradox is not resolved until one final act, the act of observation. We, the scientists, the curious, the ones who set this grim experiment in motion, reach out and unlatch the box. We lift the lid, light floods the interior. Our consciousness, our measuring apparatus, our simple, intrusive presence connects with the system inside. And in that instant, in a flash of cosmic decision-making so swift it defies time itself, the universe chooses. The wave function, that beautiful, complex mathematical description of all possibilities, collapses. It snaps instantly and violently into a single, definite reality. The superposition is shattered. The shimmering haze of potentiality evaporates into the cold, hard light of actuality. The quantum ghost is exorcised, and the cat is either alive, purring and blinking in the sudden light, or it is dead, a tragic, silent monument to a quantum coin toss. There is no longer any ambiguity. Reality has asserted itself. But this final step, this seemingly simple act of looking, is where the true, deep mystery begins. This is the question that transforms Schrödinger's thought experiment from a clever puzzle into a foundational crisis for physics and philosophy alike. What precisely constitutes an observation? What is the magical ingredient in looking that forces nature's hand? When exactly did that wave function collapse? This question, the measurement problem, is the gaping wound that Schrödinger's cat exposed, and it has bled for nearly a century. Physicists have been locked in a desperate search for an answer, a search that takes us to the very meaning of consciousness, reality, and the fabric of the cosmos. Think about the possibilities. Does the collapse require a conscious observer? Does the universe wait for a human being with a complex brain capable of understanding and registering the outcome to look inside? Is there something special about our brand of awareness that serves as the final arbiter of reality? This idea that consciousness itself shapes the physical world is profoundly unsettling. It suggests a universe that is not a cold, objective machine running on its own, but a participatory drama that requires an audience to write its ending. It places humanity at the very center of cosmic events, not as passive witnesses, but as active creators of the reality we perceive. If a tree falls in a forest and no one is around to hear it, does it make a sound? Quantum mechanics asks an even stranger question. If no one is looking, is the tree even fallen? Or perhaps consciousness is a red herring, a touch of human arrogance. Maybe the observer doesn't have to be human at all. Was the Geiger counter itself an observer? When its needle detected the particle, wasn't that a measurement? Didn't that interaction, a complex classical instrument recording a quantum event, suffice to collapse the atom's wave function? If so, the cat's fate was sealed long before we opened the box. The superposition would have been a fleeting, momentary thing, existing only for the atom before it met the detector. In this view, the cat was never both alive and dead. It was one or the other, and our ignorance was just that ignorance. But this raises yet another thorny question. Where do you draw the line? What makes a Geiger counter a classical measurement device, and an atom a quantum system? They are, after all, both just collections of atoms governed by the same fundamental laws. There is no clear, non-arbitrary place to draw that boundary. The schism remains. Let's go deeper. Could the cat itself be the observer? It is, after all, a conscious being. Couldn't its own awareness of its state, the feeling of warmth, the scent of the air, or the sudden final sting of the poison, be enough to collapse the wave function? If the cat is the observer, then it is never in a superposition of being, alive and dead. It is either alive and aware of being alive, or it is dead and thus unable to observe anything. This neatly solves the paradox of the zombie cat, but it leaves us with an even stranger possibility, a universe whose reality bifurcates depending on the perspective of the observer. From our perspective outside the box, the cat is in a superposition. From the cat's perspective inside, it is in a definite state. How can reality be two different things at once, simply depending on who is asking the question? Or perhaps the answer is simpler and colder than any of these. Maybe collapse has nothing to do with consciousness or complex machines. Maybe it is caused by any interaction with the environment, no matter how small. A single stray photon bouncing off the cat, a single air molecule bumping into the poison vial. The process is called quantum decoherence. In this view, the perfect isolation required for a macroscopic object like a cat to remain in a superposition is a practical impossibility. The universe is a noisy, messy, interconnected place. Information about the system inevitably leaks out into the wider environment, and that leakage is what destroys the quantum haze and forces a definite state. The observation is not a single dramatic moment of looking. It is a constant, relentless process of the universe measuring itself. The superposition of the cat, if it could exist at all, would last for only an infinitesimal fraction of a second before the environment observed it and forced a choice. The box, once a simple thought experiment, has become a coffin for classical intuition. It has locked us in a room with the most profound questions we can ask. Is reality a fixed, objective thing that exists independently of us? Or is it a fluid, participatory process that only solidifies when we look at it? Are we merely discovering the universe, or are we in some deep and mysterious way helping to create it with every glance? Schrödinger's cat was not meant to be an answer. It was meant to be a question, a challenge hurled at the heart of physics. It was a demand for a better story, a more complete picture of how the world truly works. The paradox forces a choice upon us, just as observation forces a choice upon the cat. We cannot hold both our classical everyday intuition and the raw mathematics of quantum theory in our minds at the same time without something breaking. One of them has to give. To find the answer to decide which reality we truly inhabit, physicists realized they would have to propose solutions so radical, so mind-altering, that they would make a cat that is both alive and dead seem tame by comparison. They would have to be willing to shatter our very definition of the universe itself. And so we are left here, outside the sealed chamber, suspended in the same impossible state as the creature within. The mathematics, our only reliable guide into the quantum realm, has led us to a logical abyss. It tells us with cold, hard certainty that the cat is a ghostly amalgam of life and death, a single entity described by two mutually exclusive realities. It presents a conclusion so violently at odds with our lived experience that it feels like a declaration of war on common sense itself. This is not just a clever puzzle. It is a profound crisis, a deep schism that split the world of physics right down its core. For if the fundamental laws of the universe produce this kind of madness when scaled up from an atom to a cat, then our understanding of reality is not just incomplete, it is profoundly, terrifyingly broken. The spectre of Schrödinger's paradox forced the greatest minds of the 20th century into a desperate intellectual battle, a philosophical maelstrom from which we have yet to truly emerge. They had to find a way out, an explanation for why we never ever witness such quantum weirdness in our everyday world. Why, when you finally lift the lid of that box, do you see not a blur of possibilities, but a singular, definite outcome? The search for that answer would splinter physics into warring tribes, each proposing a vision of reality more strange and unsettling than the last. The first, and for decades the most dominant attempt to resolve this insanity, is known as the Copenhagen interpretation. Championed by the titans of the field Niels Bohr and Werner Heisenberg, it is less a complete explanation and more of a pragmatic truce with the bizarre. To them, the quantum world was a realm of pure potential, a landscape of shimmering probabilities described by the wave function. The cat, the atom, the poison, all of it existed together in this haze of superposition, this delicate bubble of what could be. But they argued this ghostly state is fragile. It cannot survive contact with our large-scale classical world. The moment a measurement is made, the moment we seek to know the state of the system, the bubble of possibility pops. The wave function, they called it, collapses. Instantly, violently and irrevocably, all the myriad possibilities vanish, and only one single concrete reality crystallizes into existence. The universe at that precise moment is forced to make a choice. The atom is either decayed or not. The poison is either released or contained. The cat is either alive or dead. There is no lingering blur, no ghostly overlap. There is only the stark classical fact that greets your eyes. For many physicists, this was enough. It was a powerfully effective description of what happens in experiments. The mathematics of the wave function could predict the odds of each outcome with breathtaking accuracy, and the principle of collapse explained why we only ever see one of them. Theirs was a philosophy of sheer pragmatism. If the equations work, if they predict the results of our experiments, then that is the only truth that matters. The deeper questions, the what is really happening, questions that tormented Einstein and Schrödinger, were dismissed by some as unscientific as meaningless semantic games. The universe, according to this view, simply doesn't have definite properties until we look at it. Before the measurement, it is nonsensical to even ask if the cat is alive or dead. The question itself is invalid. The property we call life, or death, is not a pre-existing fact waiting to be discovered. It is an attribute brought into being by the very act of our observation. We are not passive witnesses to reality. We are active participants in its creation. Every time we measure a quantum system, we are like cosmic sculptors, forcing a block of raw, undefined potential to take on a single, sharp-edged form. It's a powerful and functional idea, one that underpins much of the technological miracle of the last century. But Schrödinger's thought experiment was designed precisely to expose the colossal ambiguity hiding at the heart of this interpretation. It screams out a single devastating question: what exactly constitutes a measurement? What is the magical ingredient in an observation that has the power to shatter the quantum dream state and forge a single reality? The Copenhagen interpretation is maddeningly silent on this crucial point. Does the collapse require a conscious human mind? Does the universe wait for you specifically to open the box and peer inside before it makes up its mind? This seems to grant humanity a privileged central role in the cosmos that science has spent centuries trying to dismantle. If a scientist looking at a screen causes the collapse, what about a laboratory camera that records the result? Does the wave function collapse when the light hits the camera's sensor, or does it collapse only when the scientist later watches the recording? The problem spirals into absurdity. Let's follow the chain of events inside the box. The radioactive atom is in a superposition of decayed and not decayed. It is linked to a Geiger counter. Is the Geiger counter a sufficient measuring device to collapse the atom's wave function? If it is, the paradox is solved before it even begins. The cat's fate is decided the instant the counter clicks, or doesn't click. But what makes a Geiger counter so special? It's just a collection of atoms obeying the same quantum laws as everything else. So perhaps the Geiger counter too enters a superposition of having clicked and not clicked, entangled with the atom's state. This joint superposition then triggers a hammer, which is also just a collection of atoms. Does the hammer then exist in a superposition of falling and not falling, which then shatters a vial existing in a superposition of broken and intact, which releases a poison in a superposition of spreading and not spreading? See the problem. There is no clear place to draw the line. There is no logical boundary where the strange rules of the quantum world cease to apply, and the familiar rules of our classical world take over. This boundary, which physicists call the Heisenberg cut, is entirely arbitrary. The Copenhagen interpretation demands that this cut exists, that there is a line separating the quantum observer from the quantum observed, but it offers no principle whatsoever to tell us where that line should be drawn. Is the cat itself an observer? Its complex biological system is certainly interacting with its environment. Could the cat's own consciousness, or even just its cellular machinery, be enough to collapse the wave function and seal its own fate long before we ever open the box? If so, the cat is never in superposition. But then, what about a simpler organism, like an amoeba, or a virus, or even just a complex non-living molecule? Where does the power to collapse reality begin? Schrödinger's cat holds a mirror up to the Copenhagen interpretation, and the reflection reveals a deep philosophical crack. It works, yes, but it feels incomplete, like a powerful spell for which we have the words but no understanding of the underlying magic. This deep dissatisfaction, this feeling that reality should not be dependent on such ill-defined concepts as measurement, drove a young, audacious physicist named Hugh Everett III to propose an alternative in the 1950 seconds. It was an idea so radical, so breathtaking in its scope, that it was initially dismissed as science fiction. Everett looked at the central equation of quantum mechanics, the Schrödinger equation, and took it to its ultimate, terrifyingly literal conclusion. He saw how the wave function beautifully described the evolution of a system into a superposition of multiple states, the atom decayed and not decayed. The Copenhagen interpretation introduced a second ad hoc rule that this smooth evolution is violently interrupted by a collapse upon measurement. Everett asked a simple revolutionary question. What if it isn't? What if there is no collapse? What if the wave function always evolves smoothly and perfectly according to Schrödinger's equation, without any sudden, mysterious pops or jumps? If that were true, then all the possibilities contained within the superposition must in some sense be equally real. When you open the box, you don't cause reality to choose one path. Instead, you become part of the system. Your own wave function becomes entangled with the cat's. At that moment of observation, the entire universe, including you, cleaves in two. In one branch of reality, you open the box and find a cat that is alive. The atom didn't decay, the poison was never released, and in this universe you feel a sense of relief. But in another perfectly parallel branch of reality, a duplicate version of you opens an identical box and finds that the cat is dead. The atom did decay, the tragic sequence of events unfolded, and that version of you is confronted with a grim outcome. This is the many worlds interpretation. It posits that there is no collapse, only a constant, continuous and exponential branching of reality. Every quantum event that has more than one possible outcome causes the universe to split into multiple copies, one for each possibility. The wave function never collapses. It simply describes the ever-expanding collection of all these parallel worlds. The sheer ontological extravagance of this idea is difficult to comprehend. It means that you right now are constantly splitting into countless versions of yourself. There is a universe where you turned left this morning instead of right. A universe where you took that other job, married that other person, or never even existed. Every choice, every random quantum fluctuation in the cosmos spawns an entire new timeline, a complete and distinct universe. The cat in the box isn't in a superposition of alive and dead in times our time's world. Rather, before the box is opened, there is simply one world containing the unopened box. After it's opened, there are two worlds, one with a living cat and a happy observer, and one with a dead cat and a grieving observer. Both outcomes happen. Both are completely real. We only experience one of these branches because our consciousness is confined to a single path. We are riding one particular storyline through this immense cosmic, choose-your-own-adventure book, blissfully unaware of the infinite other stories being written on parallel pages. The many worlds interpretation solves the measurement problem with brutal elegance. There is no arbitrary Heisenberg cut, no mysterious collapse, and no special role for consciousness. Everything from a subatomic particle to a galaxy to a human observer is governed by the exact same universal quantum laws. The theory is clean, deterministic, and follows directly from the mathematics without any extra assumptions. But it comes at a staggering price, an infinite number of unobservable parallel universes. This is its greatest weakness and the primary source of criticism. How can we ever prove that these other worlds exist if they are by definition causally disconnected from our own? They are beyond the reach of any experiment we could ever devise. Science relies on falsifiability, on the ability to test a hypothesis and prove it wrong. Many worlds, its detractors, argue steps outside of science and into the realm of metaphysics. It presents us with an infinitely complex and majestic vision of reality, but one that may forever remain a matter of faith rather than fact. It replaces the mystery of the collapse with the seemingly untestable assertion of a near-infinite multiverse. We have escaped the paradox of the cat, but at the cost of sacrificing a singular shared reality, caught between the pragmatic but incomplete Copenhagen view and the elegant but untestable many-worlds theory. A third path emerged. These are the objective collapse theories, a family of ideas that attempt to find a middle ground. They agree with Copenhagen that the wave function really does collapse, but they profoundly disagree about the cause. For proponents of objective collapse, the collapse is not a result of measurement or consciousness. It is a real, physical and spontaneous process that is written into the laws of nature itself. The idea is that Schrödinger's equation as we know it isn't the whole story. It's a brilliant approximation, but it's missing a term, a subtle new piece of physics that causes superpositions to naturally fall apart on their own. According to these models, collapse is a matter of scale and complexity. A single isolated particle like an electron can maintain a superposition for a very long time. Its wave function is stable. But as a system grows larger and more complex, involving millions, billions, trillions of entangled particles, like for instance a Geiger counter, a hammer or a cat, it becomes increasingly unstable. Think of it like a pencil balanced perfectly on its tip. A tiny microscopic quantum system is like a very short stubby pencil. It's relatively easy to keep it balanced in its precarious state of potential. But a macroscopic object like a cat is a vast, interconnected system of countless particles. It's like an impossibly tall, thin pencil. The slightest random fluctuation is enough to make it wobble, and its own sheer complexity makes it destined to topple over into one definite state or another. The collapse in this view is an inevitable consequence of size. Superposition is a delicate condition that simply cannot survive at the macroscopic level. It's not that we can't see a cat that is both alive and dead. It's that the universe itself has a physical law that forbids such a large-scale object from remaining in that state for any meaningful length of time. This approach has one enormous advantage over its rivals: it is testable. Unlike the philosophical debate over what constitutes a measurement in the Copenhagen interpretation or the untestable existence of other universes, in many worlds objective collapse theories make concrete physical predictions. If wave functions are spontaneously collapsing all the time, this process should not be perfectly clean. It should generate a tiny amount of energy, a very faint universal background hum or warming effect. It also predicts that the laws of quantum mechanics might begin to show tiny deviations under very specific experimental conditions where a system is pushed right to the edge of the microscopic and macroscopic boundary. For decades, these effects have been far too small to detect, but experimental physics is catching up. We are now building quantum systems of unprecedented size and complexity, systems that live in the twilight zone between the world of the atom and the world of the cat. Experiments in laboratories around the world are pushing the limits, trying to hear that faint cosmic hum, searching for the telltale evidence of spontaneous collapse. If they find it, it will be one of the greatest discoveries in the history of science, a new law of nature that finally bridges the quantum and classical worlds. If they don't, it will only deepen the mystery further. So we stand at a crossroads, presented with three profoundly different visions of our universe, each born from the enigma of that single unfortunate cat. Is reality a set of potentialities that only becomes concrete when we look as the Copenhagen interpretation suggests? A reality where our observation is the anchor that moors the ship of existence in a single harbour? Or is it an ever-branching river of timelines, as many worlds imagines a cosmos of infinite possibility, where every outcome is realized somewhere, and we are but one current in an endless ocean? Or finally, is reality governed by a hidden law of nature? As objective collapse theories propose, a universe where the ghostly quantum state naturally and inevitably decays into the solid classical world we know, like a radioactive isotope shedding its instability. A collapse upon measurement, a splitting of universes, or a spontaneous physical decay. Each path out of the paradox leads to a fundamentally different cosmos. Each carries with it a cascade of philosophical and scientific baggage. And each represents a front line in the ongoing war for the soul of reality. The cat in the box did more than threaten the life of a hypothetical animal. It exposed the terrifying fact that we, its keepers, have no consensus on the nature of the world outside the box. The puzzle isn't just about what happens inside that chamber of doom. The puzzle is about us and the very fabric of the cosmos we inhabit. And as we continue to probe the quantum realm, moving from thought experiments to building real machines that harness this strange power, the need to choose a path or find a new one entirely becomes more urgent than ever before. And so we were left adrift in a sea of ideas, a philosophical maelstrom, where parallel universes branch into infinity, where a hidden reality guides particles like a phantom current, where consciousness itself might be the agent that solidifies existence from a mist of probability. For decades, these interpretations of quantum mechanics were just that, interpretations. Untestable, unfalsifiable stories we told ourselves to make sense of the mathematical truth. The debate between Bohr and Einstein, between Everett and Bohm, seemed destined to remain a stalemate, a grand intellectual exercise confined to blackboards and thought experiments. The cat, it seemed, would remain suspended in its paradoxical coffin forever, its fate decided only in the abstract realms of human imagination. But while the philosophers argued, the engineers were building. In the quiet cold of shielded laboratories, a revolution was taking shape, one that would finally drag this esoteric debate out of the ivory tower and into the crucible of physical reality. The question was no longer just what it all means, but whether we could build machines precise enough, sensitive enough to force the universe to show its hand. We were about to stop asking questions and start building the answers. The first great challenge was a matter of scale. Superposition in a single electron, a lone photon, was one thing. This is the quantum world's native territory. But Schrödinger's thought experiment was so profoundly disturbing precisely because it took this microscopic uncertainty and chained it to a macroscopic creature. To truly confront the paradox, we had to bridge that chasm. We had to find a way to coax not just a single particle, but a collective, a intangible object composed of trillions upon trillions of atoms into that ghostly state of being and not being. This is the frontier of the mesoscopic world, the twilight kingdom between the atom and the apple, where the classical rules we live by begin to fray, and the bizarre laws of the quantum can, if you are careful, be made to hold sway. In a laboratory at the University of California, Santa Barbara scientists constructed something extraordinary. It looks to the naked eye like a tiny metallic paddle, a sliver of aluminum no bigger than a grain of sand etched onto a silicon chip. But this is no ordinary sliver of metal. It is a quantum drum, a mechanical resonator engineered with almost supernatural precision. Cooled to within a hair's breadth of absolute zero, entombed in a vacuum more perfect than deep space, this tiny drum is shielded from the relentless noise of our classical world. Every stray vibration, every errant particle of heat, every whisper of electromagnetic radiation is a hammer blow that could shatter the fragile state they hope to create. The goal is audacious: to make this visible object, this solid thing, vibrate and not vibrate at the very same time. Using microwaves, the researchers gently nudge the drum, not with enough energy to make it definitively oscillate, but with a precisely calibrated pulse that places it into a superposition of states. The math is unequivocal. For a fleeting moment, the tiny paddle, an object composed of over 1 trillion atoms, exists in a quantum blur. It is both moving and perfectly still. We have created a macroscopic Schrödinger's cat, not of flesh and blood, but of aluminum and silicon. We cannot, of course, look at it directly. The very act of measuring its position with a laser would, just as with the original cat, force it to choose. The wave function would collapse. Instead, its state is delicately inferred by how it interacts with a specially prepared quantum bit, a qubit that acts as our proxy observer. The experiment is a monumental achievement. It proves that quantum mechanics is not just for the invisibly small. Its strange rules can apply to objects large enough to be seen, bringing the paradox out of the realm of pure thought and placing it onto the laboratory bench. But what if we could go further? What if the key to understanding reality isn't just in making one thing exist in 2 states at once, but in linking the fates of 2 separate things across any distance? This is the promise of entanglement, Einstein's spooky action at a distance, and it has become the engine of the next great technological leap. The cat in the box was linked to a single radioactive atom. Its fate was binary, tied to a single quantum event. But what if we could create a system of not one but dozens, hundreds, or even thousands of quantum bits, all intricately link their fates, woven together in a complex tapestry of shared probability? This is the foundational principle of a quantum computer. A classical computer bit is a simple switch, a 0 or a 1. It is a world of absolutes. A quantum bit, or qubit, however, can be a 0, a 1, or crucially both at the same time, thanks to superposition. When you have 1 qubit, you have 2 possible states. But when you have 2 qubits because of entanglement, you don't just have 4 states. You have a single system that exists in a superposition of all 4 possibilities simultaneously. With 3 qubits, it's 8 states. With 300, the number of states it can explore at once is a 2 followed by 90 zeros, a number greater than all the atoms in the known universe. A quantum computer, therefore, is not just a faster version of the machine on your desk. It is a fundamentally different kind of reality engine. When we ask it to solve a problem, it doesn't try one solution after another. It leverages the almost infinite canvas of superposition and entanglement to explore every single possible solution simultaneously. It is like having a choir of a billion ghosts all singing a different note at once and being able to listen for the one single harmony that represents the correct answer. In laboratories run by giants like Google and IBM, these machines are now a reality. They are stunningly complex contraptions, arrays of superconducting circuits suspended in magnificent golden chandeliers cooled by liquid helium to temperatures colder than interstellar space. They are for now noisy and prone to error. The very act of maintaining this delicate multi-particle superposition, this global quantum state, is a constant battle against the universe itself. The environment is always listening, always trying to measure the system, always trying to force a collapse. This relentless intrusion is called decoherence. It is the process by which the quantum dream dissolves upon contact with the waking world of classical physics. And in fighting it, in learning how to shield these qubits and build error correction into their logic, we are learning more than just how to build a better computer. We are learning precisely what it takes to keep the cat in its box alive and dead, and what forces are constantly trying to open the lid. The implications are staggering, promising to revolutionize everything from medicine and material science to artificial intelligence. But for our quest, the quantum computer serves a more profound purpose. It is the ultimate laboratory for studying the measurement problem. Each calculation it performs is a grand-scale Schrödinger's cat experiment. We prepare an elaborate superposition of states, let it evolve, and then at the very end we perform a measurement. We open the box. We force this vast, intricate wave function, holding more information than all the classical computers on Earth combined, to collapse into a single definite answer of zeros and ones. We are becoming masters of collapse, turning the central mystery of quantum mechanics into a tool. We are learning to walk the tightrope between the quantum and the classical, and in doing so, we are gathering unprecedented data on the nature of the boundary itself. Where does the quantum end and the classical begin? The quantum computer answers it ends wherever we are not careful enough to prevent it. The divide is not a wall, it is a porous membrane, and we are finally learning how to control what passes through. This new power, this ability to induce and maintain quantum states in complex systems, inevitably pushes us toward the most provocative frontier of all life itself. Schrödinger chose a cat for a reason. Its living, breathing complexity represented the ultimate classical object, the antithesis of a fuzzy, uncertain electron, the chasm between the quantum jitter of a single atom and the definite integrated reality of a biological organism seemed absolute. But is it? Could life in fact not be the antithesis of the quantum world, but its most sophisticated expression? The question is no longer purely philosophical. We are now performing experiments that place this very idea on the line. At the University of Vienna, scientists have taken large, complex organic molecules compounds, with hundreds of atoms, the building blocks of life, and have successfully sent them through a double-slit experiment. The results are astounding. These intricate molecules, far larger and more complex than any simple particle, create an interference pattern. Each molecule, in some sense, went through both slits at once. The principle of superposition holds. The weirdness isn't confined to the inorganic world, and now the experiments are becoming even more audacious. Scientists are proposing, and in some cases, attempting to place an entire living organism into a state of superposition. The candidate for this incredible feat is a microscopic creature known as a tardigrade or water bear. These eight-legged invertebrates are nature's ultimate survivors, capable of entering a state of suspended animation where they can withstand extreme temperatures, radiation, and the vacuum of space. The plan is to cool a tardigrade to near absolute zero, placing it in this dormant state and then coupling it to a superconducting qubit. The goal is to entangle the biological state of the tardigrade with the quantum state of the qubit. If the qubit is in a superposition of 0 and 1, then the tardigrade, by extension, would be entangled with it entering a superposition of what exactly? Two slightly different metabolic states, two infinitesimally different positions, we don't yet know. But the very fact that we can design such an experiment is a paradigm shift. We are on the verge of creating a true biological Schrödinger's cat. This brings the paradox to its most intimate and unsettling point. If a living thing can be in a superposition, what does that say about the role of consciousness? John von Neumann and Eugene Wigner famously proposed that it is the act of conscious observation that ultimately collapses the wave. Function. The cat is neither alive nor dead until a conscious mind registers its state. For most physicists, this idea has always felt like a step too far, an unnecessary injection of mysticism into physics. But our new experimental capabilities might allow us to test it. One proposed experiment, a complex variation of the Wigner's friend thought problem, imagines a quantum system being measured by an observer. Let's call her Alice, who is herself inside a perfectly isolated laboratory. From Alice's perspective, she measures the system and collapses its wave function to a definite state. But from the perspective of another scientist, Wigner, outside the sealed lab, the entire system, Alice, her measuring device, and the quantum particle is now one large entangled superposition. It is only when Wigner opens the lab and asks Alice what she saw that the time's entire time system's wave function collapses for him. So when did the true collapse happen? When Alice made her measurement, or when Wigner made his? Or do both outcomes exist in separate branches of reality, as the many worlds interpretation would suggest? For the first time, we can conceive of real-world experiments, perhaps using advanced artificial intelligence as the conscious observer inside the box that could distinguish between these possibilities. We could, in principle, perform a delicate measurement on the entire sealed lab times before times opening it to see if it truly is in a state of superposition. Such an experiment would push our technology to its absolute limits, requiring a level of control over decoherence that is currently beyond our grasp. But it is no longer science fiction. It is a technological roadmap. We are designing a trial where the defendants are the very interpretations of reality itself. On one side stands the Copenhagen interpretation, which posits a real, irreversible collapse upon measurement. On the other, many worlds, which insists no collapse ever occurs, only a branching of universes. And in the wings are other contenders, each predicting subtle deviations that we are now gaining the power to detect. The courtroom is being built. The evidence is being gathered. Every time we sustain a superposition in a quantum drum, every time we run a calculation on a quantum computer, every time we nudge a biological molecule toward a quantum state, we are sharpening our questions and refining our tools. We are learning that the classical world we perceive is not fundamental. It is an emergent property, a consensus reality that arises from the ceaseless, incredibly rapid process of decoherence. The universe is constantly measuring itself, and the boundary between the quantum and the classical is simply the point where systems become too large, too warm, too complex, and too entangled with their environment to maintain their quantum purity. The collapse may not be a sudden magical event, but a gradual leaking of quantum information into the surrounding world, a process we are finally beginning to map and understand. We have not yet delivered a final verdict. We have not yet definitively proven one interpretation right and all others wrong, but we have transformed the nature of the inquiry. The question of Schrödinger's cat is no longer a philosophical game. It has become the central driving force behind a technological and scientific revolution. We have taken the abstract ghost that haunted the dreams of the quantum founders and are slowly, painstakingly dragging it into the light. And what we are discovering is changing not only our vision of the universe, but our understanding of the very dividing line between what is real and what is merely possible. The next step is to ask what this new, deeper reality means for us, the conscious minds that perceive it and are perhaps an inseparable part of it. And so, after our long descent into the quantum looking glass, we return at last from the tenebrous confines of that infamous box. We have journeyed through the thought worlds of giants, wrestled with waves of probability, and stared into the abyss, where common sense dissolves into a shimmering ghost of potential. What we have found is that Schrödinger's cat, in its terrible, elegant simplicity, was never truly about the fate of a feline. It was never an experiment meant for a laboratory, but rather one designed for the mind, a philosophical crucible forged to test the very metal of our understanding. Erwin Schrödinger, in his brilliant frustration, did not give us a mere puzzle. He gave us an intellectual scalpel, a tool sharp enough to dissect the assumptions underpinning our entire perception of the universe. With it, we have been forced to slice open the comfortable carcass of classical certainty and gaze upon the bizarre, vibrant, and profoundly unsettling organs of the quantum world within. The legacy of this thought experiment is not a solution, but a persistent and essential question that echoes down the halls of science, a question that has become the engine of discovery itself. The cat is the eternal ghost in the machine of physics, a stubborn paradox that refuses to be exorcised, reminding us with every spectral purr that our most successful theory of reality is at its heart magnificently, terrifyingly strange. It has transcended the arcane pages of physics journals to become a cultural touchstone, a universally recognized symbol for profound uncertainty for the delicate and often bewildering state of being caught between two worlds. When we speak of the cat, we speak of the tension between what could be and what is, a tension that defines not only subatomic particles, but so much of our own existence. This journey forces upon us a reflection that extends far beyond the equations. It compels us to confront the most fundamental philosophical schism in human history, the very nature of reality. For millennia, we lived in a Newtonian cosmos, a grand and predictable clockwork mechanism wombed by God or by initial conditions, ticking along its deterministic path, whether we were there to watch it or not. A planet had a position, a ball had a trajectory. Reality was a solid, objective fact, and our science was the slow, noble process of uncovering its immutable laws. But the cat in its state of quantum limbo shatters that clockwork. It presents us with a universe that is not a finished masterpiece, waiting to be admired, but an interactive canvas, a participatory drama in which the act of observation is a critical creative force. The paradox whispers a profound and unsettling suggestion that reality at its most fundamental level might be conditional, a sea of potentialities that only crystallizes into definite existence when a conscious mind, or at least a measuring device, intervenes. This is a terrifyingly anthropocentric idea, one that seems to place humanity, or at least the act of measurement, at the very center of the cosmic story. Are we merely passive spectators, or are we in some inexplicable way the midwives of reality? Are we the agents who, by the simple act of looking, force the universe to make a choice, collapsing the shimmering wave of maybe into the solid particle of now? This is the measurement problem in its most stark and personal form. It shifts our role from cosmic archaeologists dusting off the pre-existing truths of the universe to that of cosmic collaborators whose engagement helps to write the next line of the story. The Copenhagen interpretation, with its stark dividing line between the quantum and classical worlds, asks us to simply accept this strange duality, to be content with the power of our mathematics to predict outcomes without ever truly explaining the underlying mechanism. Yet the human mind rebels against such an arbitrary boundary. Why should the rules that govern an atom suddenly break down when that atom becomes part of a Geiger counter, or a vial of poison, or a cat? The sheer audacity of the many worlds interpretation we explored is a direct response to this discomfort, an attempt to preserve the integrity of the quantum equations by sacrificing the singularity of our own reality. In that view, the universe does not choose, it does everything. Every possible outcome of every quantum event splits the cosmos into a new parallel timeline, a universe where the cat lives and one where it dies. Our consciousness, our perception of a single coherent story, is merely the path we happen to be navigating through this infinitely branching garden of cosmic histories. It is an idea of breathtaking scope, one that renders our own lives both infinitesimally small and infinitely related. The cat in this context is not a victim of paradox, but a nexus of creation, the point at which entire realities are born from a single quantum flicker. Even the more pragmatic theory of decoherence, which seeks to explain the transition from quantum to classical through the interaction of a system with its environment, carries its own deep philosophical weight. It suggests that the strangeness of superposition is not truly erased, but is instead diluted its coherence, smeared out into the vastness of the surrounding universe. The information about the cat's dual state is not lost. It simply becomes hopelessly entangled with the trillions upon trillions of particles in the box, the air, the walls and beyond, leaking out into the cosmos like a whispered secret, impossible to reconstruct. In this view, reality becomes a matter of perspective and scale. From the God's eye view of the entire universal wave function, perhaps superposition is all there is. But for us, beings hopelessly entangled with our environment, this pure quantum state is an inaccessible dream. We can only ever perceive the classical decohered shadow it casts. We are prisoners of our own macroscopic scale, able to glimpse the true ghostly nature of things only through the narrow bars of our experiments, before the universe at large smudges the details away. The paradox remains simply shifted from a question of measurement to a question of information of where the quantum world truly ends and our classical world begins. It is not a clean break, but a messy, gradual bleeding of probabilities into certainties. And it is precisely this messy, paradoxical frontier that now powers the dawn of a new technological age. The very quantum weirdness that Schrödinger found so absurd, so philosophically untenable, is now being harnessed as the single greatest resource for the future of computation. A quantum computer does not run on simple ones and zeros. It runs on qubits, the technological embodiment of Schrödinger's cat. Each qubit exists in a delicate, controlled state of superposition, a complex blend of both 1 times and times 0 simultaneously. A quantum computer with just a few hundred of these qubits can hold and process more information, more parallel states, than there are atoms in the known universe. It is an engine built from the logic of ghosts, a cathedral of calculation founded upon the bedrock of uncertainty. The great challenge for quantum engineers is a familiar one. They must fight a constant battle against decoherence. They must build the perfect isolated box, shielding their fragile qubits from the slightest stray interaction with the outside world, lest the environment measure their state and collapse all that computational power into a single mundane classical bit. The quest to keep the quantum cat alive and dead at the same time is no longer a thought experiment. It is the central driving problem of 21st century technology. We are learning not to resolve the paradox, but to command it to ride the wave of quantum probability and steer it toward unimaginable discoveries in medicine, materials, science, and artificial intelligence. Beyond technology, the paradox continues to serve as our most reliable quantum compass, pointing the way toward the deepest theoretical questions that remain. It is the persistent itch that prevents physicists from becoming complacent, a stark reminder that our 2 great pillars of modern physics, general relativity and quantum mechanics, remain fundamentally incompatible. General relativity describes a smooth, deterministic spacetime, a stage where events happen at definite locations. Quantum mechanics describes a fuzzy, probabilistic world beneath that stage, one where location and certainty are luxuries. How can these 2 realities coexist? The search for a theory of everything, a grand, unified theory that would weave together the physics of the very large and the very small, is in essence a quest to finally and truly resolve the cat's fate. Such a theory would have to explain how times the quantum wave function collapses, or if it even does. It would have to provide the ultimate rulebook for how the ghostly world of probability gives rise to the solid world of our experience. The paradox is the proving ground for every new idea, from string theory to loop quantum gravity. Any contender for the final theory must first be able to walk up to that box, peer inside, and tell us a coherent, satisfying story about what it sees. This quest now extends to the farthest reaches of the cosmos and the most intimate corners of biology. Quantum cosmologists ponder the birth of our universe, asking if the Big Bang itself emerged from a quantum fluctuation, meaning the entire cosmos was once in a superposition of states, a universe that existed and didn't exist. Simultaneously, did the universe itself have to be observed to come into being, and if so, by what? The questions spiral into a dizzying recursion of cause and effect. Meanwhile, the emerging field of quantum biology is investigating whether the tricks of superposition are not just the domain of physicists, but have been harnessed by life itself. Could the uncanny efficiency of photosynthesis depend on electrons simultaneously exploring all possible pathways to a reaction center? Do migratory birds use quantum entanglement in their retinas to see the Earth's magnetic field, navigating with an internal compass built from this very paradox? Life, it seems, may have learned to exploit the secrets of the cat long before we ever thought to ask the question. We may be surrounded by and even composed of systems that are actively leveraging the very ambiguity we find so confounding, turning the universe's foundational uncertainty into a biological advantage. The quantum world is not a distant alien realm. It is the very substrate upon which the familiar tapestry of our world is woven, and the cat's ghost haunts every thread. So we are left here at the end of our journey, not with a neat solution, but with a deeper, more profound appreciation for the mystery. Schrödinger's cat is more than a paradox. It is a monument to the limits of human intuition. It stands as a testament to our courage to follow our theories wherever they lead, even when they guide us to the precipice of the absurd. It teaches us that the universe is under no obligation to make sense to our classically tuned minds. The quest to understand the cat's state is in the end the ultimate scientific and philosophical endeavor. It is a search that encompasses the origin of the cosmos, the architecture of reality, the future of our technology, and the very nature of our own consciousness. It is the modern manifestation of the oldest questions we have ever dared to ask. What is real? What is our place in it all? And what happens when we dare to look? The box in many ways remains closed. The most fundamental questions linger unanswered, but the act of asking the relentless, passionate human desire to know is what illuminates the darkness. The cat, whether living, dead, or both, has led us to the frontier of knowledge, and it is here in this shimmering space between what is known and what is unknowable that the true adventure of science begins. The search for its final truth is the search for our own.